Welcome back to the Mechanics of Solid lecture series. In this video we will complete the example that we started in the last video, which was this rotating rigid bar as shown on this page. Let's remind ourselves of what we solved for in the last video. We found the relation between F1 and F2 based on equilibrium, as well as the compatibility equation shown here. So what we're going to do is start with the compatibility equation to find a direct relation between the internal forces F1 and F2 by substituting in the known values for L, the lengths, the areas, and the elastic modulus. We're going to work in the units that are given for length in millimeters and elastic modulus in gigapascals. It doesn't matter too much what we do here as long as we are consistent, because as we will see, the units will cancel out of this equation. So let's go over here to do our work and substitute in the known values. F1, L1 is 720 millimeters, A1 300 millimeters squared, times elastic modulus of 105 gigapascals. Set that equal to negative 2 F2 times L2 940 millimeters divided by A2 200 millimeters squared times E2 210 gigapascals. And as I mentioned, the units completely balance out on the two sides. So I got millimeters on both sides, millimeters squared on both sides, and gigapascals on both sides. So I can cancel them out without any further concern. So these numbers, 720 divided by 300 over 105, you plug those into your calculator, 0.0229 times F1 equals something like negative 0.0448 F2, carrying about 3 significant digits. This further reduces to F1 equals negative 1.95 F2. Okay, now we're going to take that and substitute it into the equilibrium equation to solve for F1 and F2. And we'll have negative F2 times 420 mm plus F1, which is negative 1.95 F2 times 840 mm, carrying my units through now, minus the 33,750 kilonewton millimeters equals 0. We can cancel out our millimeters from all terms in the equation. Let's group the terms that multiply F2, negative 420 minus 1.95 times 840 equals 33,750 kilonewtons, bringing that over to the right hand side, and we get F2 equals 33,750 divided by the negative of this summation, which is 2058. So this reduces to negative 16.4 kilonewtons. The negative sign, of course, tells me that member is in compression, which I will denote with a C. Okay, coming back over here, F1 equals negative 1.95 times F2, or negative 16.4 kilonewtons, which is right about 32.0 kilonewtons, and the positive number tells me that it is tension. We carry out the same number of significant digits in both cases. Now to solve for the stresses, we just need to multiply these divide these internal forces by the areas. Sigma equals F over A. Sigma 1 equals F1 over A1. Remember that for stresses in SI, I always want to work with units newtons, millimeters, and megapascal. 1 megapascal is a newton per millimeter squared. So F1, I'm going to convert that 32 kilonewtons to 32,000 newtons divided by the area, 300 millimeters squared, gives me a stress of 107 megapascals. For my sanity check, this is a reasonable number for stress. It's large, but it's less than yield for most materials, so that seems to be a reasonable answer. As well as I can see that as I pull on point D, bar 1 is going to stretch or elongate and be in tension, giving me a positive stress. So the sign makes sense. Sigma 2, negative 16.4 kilonewtons, or 16,400 newtons, divided by the area, 200 millimeters squared, gives me a negative 82 megapascals. Number also makes sense, and the sign makes sense for the same reasons discussed earlier. And we'll skip to a clean sheet to do our final step, which is to solve for VD. And we remind ourselves of the compatibility relations we found earlier between VB, VC, and VD. So we said that VD equals 3.21 V sub B, which was related to the shortening of member 2. VD is negative 3.21 delta 2. Let's go ahead and substitute that in. VD is negative 3.21 using my FL over AE. This is F2L2 over A2 E2. We can save ourselves a little bit of work by recognizing that F2 over A2 is the stress that we just solved for. So negative 3.21 times negative 82 megapascals times the length of member 2, which is 940 millimeters, divided by the elastic modulus. And here I need to be careful to keep the units consistent. E2 at 210 gigapascals needs to be converted to megapascals. So 210 times 10 to the third megapascals, so that those two units can cancel. We're left with units of millimeters, which is what we expect for a deflection. And with all the punching all those numbers into the calculator, you would get something like 1.18 millimeters, keeping 3 significant digits. And this is also a reasonable answer for my sanity check. It's a small number. I expect deflections to be small. It's positive based on the load. And that concludes this example.